Welcome to the third lecture in software testing. As I noted before, the purpose of these lectures are to give you a general background in software testing and also to make it quick. Last class I showed you this chart which shows the universe of static testing and dynamic testing. Last time we discussed static testing. Today we're going to discuss dynamic testing. I'm going to show you a number of techniques that are going to make it easy for you to prepare test cases. Let's start with equivalent class analysis. An equivalent class consists of a set of data that should produce the same result. If one test case in the equivalent class detects a defect, all other test cases in the same equivalence class are likely to detect the same effect. If one test case in an equivalent class does not detect a defect, no other test cases in that same equivalent class is likely to detect the defect. So what do I mean? As before, we're going to go through an example where things should become a little bit clearer. Okay, program requirements. The program calculates the commission earned by the salesman. If 10 or less units are sold, then the commission for the salesman is going to be 10%. If more than 10 units are sold but less than 100, then the commission for the salesperson is going to be 8%. If more than 100 units are sold, then the commission will be 4%. Maximum number of units for each sale is going to be 500 units. So let's look for equivalence classes for this program. So what I'm showing here is a table where we're going to put the class number, the requirements associated with that class. Then we'll put in valid values and also invalid values. Invalid values are very important. They are as important as the valid values. So for class 1, we say if less than 10 units are sold, then the commission is 10%. So what we have here is the valid values for this is going to be between 0 and 10 units. Now the invalid values are going to be the negative numbers less than 0, fractions, letters, and symbols. Now we identify a second equivalence class, which is if more than 10 units are sold but less than 100. So valid values here are going to be 11 through 99. Invalid values are going to be negative numbers, fractions, letters, and symbols. So here we identified a third class, which is if more than 100 units are sold, then the commission is 4%. Now, the valids are going to be numbers between 100 and 500. Invalids will be negative numbers greater than 500, fractions, letters, and symbols. So what we've done so far is we've identified our equivalence classes. So now before I go further into this example, I would like to talk about boundary analysis. Boundaries are where many defects hide. So basically you could look at this. If you are on a steady state, then something happens and then you go to a different state. This where something happens is the boundary, and that's where most of the defects hide. The boundaries are there are boundaries between equivalence classes. The biggest or smallest value that can be inputted into a program input data that will generate the bigger and smaller outputs. So let's go back to our example and see where our boundaries are. So there are boundaries between equivalence classes. So we have invalid equivalence class, equivalence class 1. We have a boundary here at 0. Between equivalence class 1 and equivalence class 2, we have a boundary right at 11. And then we have another boundary at 100 and 500. The biggest or smallest value that can be inputted into the program. Well, the smallest value can be 0. So before 0, we have a boundary right here. Between invalid and 0, we have a boundary. Value that can be inputted, the biggest number. So we have a boundary right here between 500 and invalid data. Input data can generate the biggest and the smallest number. So we want to put an input data that is going to generate the biggest number, which would be 500 or greater, so which would be the 500 valid plus the greater invalid, and the same to generate the smallest data, we would put 0 here. So let's go back to our example, so we can start selecting actual values. So we have our the requirements for our example here. Next, we have this graph, which gives us an idea what's going on. So let's start selecting values. Okay, so we have here the class and the values. So for class 1, I've selected first -1. That's the invalid data from this class. Next, I went and selected a 0.9, which is the boundary value, followed by 0, which is the valid input for equivalence class 1. Next I use the 10, which is the maximum. It's the maximum value for valid equivalence class 1. Then 10.9, which is right here at the boundary between equivalence class 1 and equivalence class 2. Then the A and the number, which is just a letter and a symbol. For equivalence class 2, I use the value 11, which is right on the boundary, a 55, which is at the middle, then the number 99, which is the other boundary value, plus an invalid 99.9, which is getting as close as possible to 100, to make sure this boundary is done correctly. And then finally, I use a small letter cap and a symbol. Now, for class 3 again, I use the 100, which is the boundary value. Then I use a 300, which is the middle of the road equivalence class 3 number, followed by 500, which is the other valid boundary value. Finally, next, I use 500.01, which is again right getting into the boundary between the equivalence class 3 and the invalid data. Then use a 501, which is a data for the invalid data right here. And then I ended up with a letter X and a symbol. Now, if this program would have been programmed like this, this is kind of a pseudo C code. So if it had been programmed like this, like if sales greater than 10 but greater than 0, less or equal than 10, greater than 10, less than 100, greater or equal to 100, less than 500, then we do the calculation for the commission. Then these numbers would be pretty good numbers. These ones here. That's the good news. The bad news is if somebody would have programmed it like this, basically an if statement for 0, 1, 2, 3, 4, 1, all the way to 100. And let's assume that he made a mistake and said sales equal to 0 equals to 1 equals to 2. And then instead of putting equal to 2 put equal to 3, and then it went equal to 5, and it just missed some of the cells values, then this set of tests would have not picked up the error. So what I'm trying to tell you is that even though we use two solid techniques, which is the identifying classes and then looking for boundary conditions, that does not guarantee that you're going to find all the errors. In this case, if somebody programmed like this, then you would have to basically do 100 cases plus over 500 and who knows how many cases to be able to cover this. Probably somebody hasn't done something coded in this fashion, but the point is that that's why software testing is so hard, and that's why you find issues. Not too long ago, I think a capsule that was supposed to go to the space station, the burn did not last as they expected. It shut off before it's supposed to and didn't get into orbit, and so we say, hey, how could those things happen? So what happened is they got to the boundary and it stopped burning when it wasn't supposed to. But those things happen is because you test your program and you don't. Sometimes it's good to just look at the code and see how this thing has been coded to make sure that your tests play okay with what those folks are doing, if possible. So anyhow, let's get to the next technique that can help you. Next technique is state transition. Okay, state transition is when your program goes from one state to another. So if you want to test the state transition, then you must understand the states of the program you are testing. So that's going to be, you're going to have to become fairly knowledgeable with the program. So anyhow, what I have here is just giving you a sample of a where you would use the state transition technique. Verify that an operating system can be loaded into the computer. The computer contains a factory loader that constantly is polling the USB interface to determine if an operating system is available. So basically what you have is a new computer that you get it from factory, and it does not have an operating system. So what it does has only a little bootloader, and what that bootloader does is constantly is checking the USB interface to see if there is a USB, and if there is a USB, then it checks to see if there is an operating system, and if it finds an operating system, it's going to load it. So let's look at the states. So the first state is something that I've called pre-operational. In the pre-operational list, you have the computer without the operating system. So it's constantly polling. It's looking at the USB to see if somebody plugs in a USB stick with an operating system. Next, when somebody does load the USB, then it changes state from pre-operational to data loading state. During the data loading state, what it's going to do is going to load all the data from the memory stick, and then it's going to load it. Now, the loading, there are two things that can happen here. It can just load the operating system completely and then install it, or maybe installing it as it loads it. So anyhow, once the data loading is complete, then the system goes into a different state, which is the operational state. So let's look at how you would test this. So first, you would verify that the polling is working. Next, you would verify the data loading. So you would install the memory stick and make sure it gets loaded into the system. And finally, what you would do is you verify that the data loading, you verify recovery from the data loading interruption. Now what this means is that you are going to interrupt the program at the middle of the data loading. Either you're going to pull out the memory stick, or you're going to remove power, or you may do both. You first test removing the memory stick and then plug it back in, and also removing power. So what you want to verify is that you're interrupting the transition from data loading to operational, and verifying that it goes back to polling. You want to make sure that you don't have a system where you remove the memory stick, or the power is interrupted, and then you lose your system completely. So anyhow, so that's the state transition, and basically you have to understand the different states of your program so you can interrupt those transitions. So let's go to the next technique, which is the race condition, looking for race conditions. Okay, when do we get race conditions? So race condition can happen if you have a multi-thread programs or distributed programs. And also another ingredient for race conditions are these two items, plus you have to be sharing a resource. The issue is that the desired sequence is broken by two processes accessing the same resource at the same time, resulting in unpredictable results. So what we have, let me give you an example. So you go to let's look at the desired sequence. So you go to your ATM machine, you enter your account, you request your balance, and then you get your money. That's the desired sequence. Okay, now let's do the operation, but this time let's take in consideration also that you had an account in Netflix, and Netflix would go and have a transaction of removing the monthly payment for your account. So let's go to our initial transaction. So you go to your ATM and you request your balance. By the time you've requested your balance and you are reading, while you are reading your balance, the Netflix transaction takes place. So Netflix gets its money. So now you have less money in your account, but you don't know it because you got your balance before that transaction. So you go and get some money, assuming that you have certain amount which you don't, and that's what's called a race condition. So you have the desired sequence was broken, and we had unpredictable results. So let's look at another example. Two persons buy an airline ticket via web. Both check what seats are available. Both select the same seat. If you have this operation, good idea is to test for race conditions. Now, race conditions are really bad news. So, first place, they are unpredictable. Next, you're going to have that something happens in the transaction and nobody can understand what happened because it's very hard to recreate. So those things will linger forever and just drive people to, I suppose, drinking. So anyhow, the point is that you have to look at the program and you have to be creative to see if you can find these race conditions. That's when you become an artist. Okay, now let's talk about load testing. Load testing is you want to test with the maximum file size. You want to save the biggest file you can save, and you want to get the biggest file from your system. And I've seen under load testing, you want to open the maximum files allowed plus one. you want to test a fully loaded data storage. So what it amounts to is when you get your telephone and whatnot, and you saved all your pictures, now the thing's not working correctly, and people say, well, the thing is almost full of data. You need to get rid of some of data before it starts behaving okay. So that's the kind of testing you want to make sure. So you want to make sure that when the person has gotten to almost the maximum loading, the thing doesn't start misbehaving. So that's what's involved in load testing. So now let's go to the last, doing error guessing. That's very important. Okay, what is the trust your instinct. You are a software engineer. You have to look at the program and you have to trust your instinct where it says where this thing is going to break. You thoroughly destructive attitude towards the program. Thoroughly, that's what you are getting paid for. Concentrate in finding test cases that show program shortcomings. You want to make the program fail. You expect the program to fail. A test that reveals a problem is a success. A test that did not reveal a problem is a waste of time. So in everything that I've showed you today, teach you today, if you blindly use this technique, you're not going to find all the errors. You need to use your gut feeling, your instinct also. It's very important. Where is this thing is going to break it? How I can break it? Okay, with that note, I'm going to end this class. So let's recap. What we learned today. So first we talked about equivalent classes. This is data that if you put one number in, if you put one number that belongs to equivalence class, the program should behave a certain way. Then we talked about boundary analysis. That's where things usually break. You go from a steady state, something happens, you go to a different state, for example. Then I talked about state transition. Your program is in one state. Then as it moves into a different state, you want to interrupt that state transitions, make sure that the system behaves when it goes, if it gets interrupted between states. Then I talked about race conditions, which are things that happen and you have to be an artist to make sure you can figure them out. And finally, I talked about error guessing, which is where you use your gut instinct, you become the software tester artist, where you look at the thing and figure out how am I going to break it. And a lot of the people that do they get into systems, they break systems. Well, they are able to break those systems, break the security because they are artists. They use this. If the testers puts a blinders, only use techniques, the bad guys that do the accessing other systems, breaking in, they could win because they are going to use their gut feelings. And so we have to not only use our techniques, but we also have to think like a software tester. We must find the error. We must destroy this program. So anyhow, I hope you folks have enjoyed this. That's the end of this class 3. For next class, I have something which is it's one of my favorite, which is going to be the structural testing. So anyhow, I hope to see you in my next class. Please subscribe to my YouTube channel so you can get notified when this happens. And happy testing. Bye-bye.